a bigger angle, it'll still bend towards the normal. You might say there's a little more bending, so it might be a little bit easier to see. That's why over here in my demonstration, I kept bending the block quite a bit so you could see it a little better. In fact, it's also why I brought these fun little demonstrations out here. These show the refraction of light, because again, I don't think it's quite as common as the reflection of the light. I'll start with this ruler. I think you're convinced it's straight, but that doesn't mean it appears to be straight. Because as the light comes out to you, it bends, but the light from here doesn't bend. If I were to take this back in this picture, I might say something, like this. Here I am standing out here. And just like the pool, looking in where it appears to be come from is different. And so as I look here, I'd say, okay, well, there's the object. It's straight, 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 straight. And the object should really go straight, but the light coming out of here bends as it goes to my eyes, and it makes it look like it's a different location. So the stuff under the water looks like it's at a different location than the stuff above the water. Of course, it's really not. It just appears that way because the light bent. And so I'll say it again, this is really not the too interesting part as it goes in, but again, just my way of hopefully convincing you it does bend. In fact, one of my favorite ones to convince you it's bent are these marbles. I'm hoping you can actually see the marbles show up here on the video camera, because these are not colored marbles. These are clear marbles. Now, if they were colored marbles, most people don't have troubles with it. They say, okay, I've got a bunch of red marbles. And of course, I got red because then the white light comes down. The red is the only color that reflects, and so they look red. And so there's an interaction between the white light and the red ones, and you go, okay, that makes sense. In fact, kind of a fun question to ask is, what color is the American flag? Most people said red, white, and blue. Okay, but we need to be careful. Why does it look red, white, and blue? It looks red, white, and blue because the red stripes are made out of a certain pigment that when you hit it with white light, in other words, when it's in the sunlight, when it's all white, and you hit it with the sunlight, all the other colors get absorbed. The only one that reflects is the red. Remember, you only see what reflects. So if you say something's red, you're going to say it's red because it reflects the red light. And then the blue background, you're going to say, well, it's blue because all the other colors get absorbed and it reflects the blue. And then the white, and you have the white stripes and the white stars. You're going to say, well, those are white because they reflect all the colors. And so you put a sunlight on it, they reflect the white. So when you put the flag out in the sunlight, you see red, white, and blue. Okay, but let me ask you this. What if you were to put that flag under a red light? What would it look like? Now, the easy one is the red stripes. The red stripes are designed to reflect red, and you only shine red light on them. That's all there is. There's nothing then to absorb, and they reflect the red. So the red stripes look red. But what about the white stripes and the white stars? See, the white stripes are designed to reflect all the colors. But you're only putting on red light. So the only thing to reflect is red. So what color would those white stripes look? And I'll call it white in quotes, because they would look red. And so you wouldn't see any stripes. You would see the red stripes looking red, but you would see the white stripes looking red. And so you would just see solid red. And what about the stars? Well, I guess they would look red. Okay, what about the blue background? Now the blue is designed to only reflect blue, but now remember, I'm only shining red on it. So it would absorb the red and then reflect nothing, because there's not blue there. Now, what would nothing look like? Well, a good example, how about you close your eyes? Put a pillow over your head and close your eyes. Don't let any light get in. That's black. And so black is your brain telling you you're not getting any light. And that's exactly what the, quote, blue background would look like. It would be black. So the blue background would look black. The white stripes and the white stars would look red. The red stripes would look red. And so an American flag under a red light would have this big area of red. Then it would have a black background with red stars. And we could even do the same thing about yellow. What if we put the American flag under a yellow light? Well, the red stripes would look black, because again, red means they only reflect red, but you're only shining yellow on it, so they absorb the yellow, you would have nothing. So the red stripes would look black. The white stripes are designed to reflect everything, so you're shining yellow on it, so you would get yellow, so you'd have yellow and black stripes. That's what you'd have. And then, of course, the stars would look yellow, and the blue background would now look black. Because they get color. Now back to this. This one's a little harder. These do not reflect or absorb. They're what we call colorless. They let the light go through them. But yet there's got to be something that makes them stand out. I mean, it's very clear when I hold this up, I have a marble here. How come this marble stands out? And I would say, not only do we see colors, but we see when the light has been affected, when the light has been shifted, when it changes direction. See, that's what we see here. We see the effect of the light shifting direction. And so these marbles are colorless, but we still see them. We see how the light coming from one side of it doesn't get bent, but the light going through it gets bent. And so it's clear, it's colorless, we like to say, but it is still being bent. It still stands out. There's edges to it. But I would say it only stands out because of the refraction. And the refraction only occurs because there is a difference of index between the marble and the air. Now I picked these marbles because they're made just right so that their index of refraction is about 1.33. And why is that important? Well, what's the index of water? 1.33. So what if these marbles were in water? You see, you wouldn't have this whole thing of refraction that I'm trying to show you. You wouldn't have the light bending at different angles because of the different way it enters. Because the marbles themselves would have an index of 1.33, and so would the water surrounding it. And so it's really fun to watch this, and I hope you'll see it on camera. If I pour water into here, they disappear. Now, are they still there? Of course they're still there, right? I'm going to reach in here and, whoops, and grab the marbles. And so there it is. You can clearly see it when the index is different between the marble and the air. But as soon as you put it in the water, there's no more bending of the light. And so this, I guess, doesn't have any marbles in it, but it just disappears. Or if you want to see them reappear, I can pour them out. And sure enough, there's all my fun marbles. And so that's, again, what I'm trying to get across. What is refraction? Why does it occur? And it's that differential in speeds. And it has an effect on the light. And as it has an effect on the light, ultimately then we can build lenses. And that's really the whole point of this chapter, is to get you to understand lenses. But like I said, there's some interesting things that can happen. And this wasn't the big interesting thing I was trying to get at. I'm trying to get at then, all right, so we've got this refraction. And that refraction can have an effect. That's how you see the marbles. But watch this. Watch when it comes out of the glass. As it comes out of the glass, something very interesting can happen. In this case, it'll bend away from the normal. And of course, in this case, it'll also bend away from the normal. But, and maybe the easiest way to show this is with my hands. Imagine the edge of this table right here. So I'm going to straighten up this table. This is the interface between in the glass. So I'll imagine I'm in the glass and I'm light. I'm in the glass trying to get out. And so I want to emphasize that this would not occur going into the glass. But going out of the glass, it could do this. So here's my beam, my arms. Okay, notice that this arm gets out first. So this one's going to go fast. And if I got all the way out, it would just kind of go like this. And so I would bend away from the normal. So I would have been coming in kind of straight, hit here, and this one would go fast, and this one would go slow. Then I would get out, and I would just go like that. But if my angle is big enough, what can happen is this one can come out and go so fast that before this one has a chance to get out, this has come all the way around, and now I'm going essentially parallel to the interface. I'm essentially half out and half in. And I wouldn't stay there because remember, this side's always going faster. I wouldn't continue to just go half out and half in. If this side could come all the way around, then as it tries to go along the interface, this is still going to travel faster, and this is going to switch it back in. And so the light doesn't actually get out. It gets trapped inside. We call this a total internal, and some people call it a total internal reflection. Some people call it a total internal refraction. I think your author calls it a total internal reflection. But regardless of what words you want to use, the end result is that it is refraction so much that it results in a reflection. And the light doesn't actually get out. Let's see if I can draw a picture of everything I was trying to show you just by walking. And then let's see if I can do a demonstration of it. And so it would look something like this in a picture. And I'll say it again, you have to be in the slower material for this to happen. So it will only happen as it's trying to get out of the glass into the air, or out of the water and into the air. So if we're in glass and trying to go into the air, and if our angle is big enough, so I'll make a kind of a big angle, then this edge right here will get out, and it'll curve around, and so you're like half out and half in. And like I said, that doesn't stop there. Then as it, you might say, well, then it's going to continue to go down. No, it won't continue to go down. It'll continue to go faster out there and curve this all the way around. And it'll be then what we like to call stuck inside. And like I said, the refraction is so much that we will call this a total internal. And let me call it reflection. And I would say most people probably call it a reflection, because the end result is the same as a reflection. But it doesn't happen because of reflections. It happens because of refractions. And so this magical one, I think I can demonstrate here. Let me try it with this thing. I'll put the lights a little bit lower. But if I put it, say, right here with my triangle, you'll see the light going in the triangle and then come out of the triangle. And I'll say it again. You can only observe this. This is only possible as it bends away from the normal, not towards the normal. So you'll never see this. This will never happen as you go into the glass. But it will happen as you go out of the glass. And so maybe you could see it a little better. I'm going to move it to this part and keep my eyes focused on that as it's coming out. It won't happen here, but watch this. As I bend it, as I make the angle coming into this interface, as it tries to get out bigger and bigger, you can actually see this beam right here, the refracted beam, bend more and more and more, and then right here, right there, boom, it's gone completely. It's all right there. It's all reflected. And so nothing gets out. Now, if I back it up a little bit, you'll see something more practical in the sense, because I've been spending this last discussion talking only about the light that goes through the interface. Remember, there's also reflection going on at the same time. And just because I talked about it in the last chapter, please don't forget it. And I think you see it well in this picture right here. Right here, maybe right before we get to this magical angle, which we're going to call the critical angle, you can hopefully see that some of the light comes out, that's the refracted light, but some of it gets reflected inside. And so I have both reflection and refraction going on at the same time. But if I keep turning it more and more, I no longer have refraction, I only have reflection. And so that's why we call this total internal reflection. All of the light reflects. But it is kind of a different reason for reflection. It is not a reflection like off these mirrors as we saw in the last chapter. This is a reflection because of refraction, a total internal refraction. But the bottom line is it still behaves like a mirror. And so the reason I bring this one up here is because today's technology of fiber optics is designed purposely with that in mind, that you can communicate on the internet and on your cell phone really well with pulses of light. And so if you put a little light right here and you blink it on and off, and the blinking pattern represents your data, and the light goes in your fiber, and your fiber is made out of glass, if that angle is steep enough, even though it hits the edge of the glass, as it moves through the glass, if it is greater than this critical angle, it will not come out of the glass. It will be trapped inside. And so this fiber optics we could run, and of course here at Santa Barbara City College, we have an excellent fiber cable that runs from the college here over to UCSB. And so I can make these pulses of light in my fiber right here in this building, and they continue. And even though this fiber goes through the walls of this building and then underground and then through the ground and then along the railroad tracks and then eventually out to UCSB and then through whatever infrastructure they have there, and it goes to their main server, all of that just follows along and it's trapped inside. Which is why then I grabbed, to help illustrate, one of our real fiber optics pieces. This is off of one of our computer networks that we've upgraded and replaced, and this would be hooked to our, I think this is the computer and this is our server, and so we could then communicate back and forth along little fibers then in here. And so maybe this part of it you can see the fibers a little better. Here's the individual fibers, although you got to be careful, these are not actually the fibers themselves. The fibers are as thin as a human hair. The plastic around them is to protect them and keep them from getting scratched or broken or damaged, because they're not very, very big. But I think there's about 24 fibers that go from here over to here. And I'll see if I can show them to you. But before I even do that, I'll just kind of cheat a little bit and say, okay, this is kind of the point I'm trying to make. This is kind of our cheapy fiber optics. I'll maybe turn down the lights behind me and maybe you can see it a little bit better. But if I take my green laser here and I shine the laser in here, it goes through this rod, if you will, pretty good. If I point the end at you, you'll see this is where the light is going through. So it's going down and it's hitting at greater than the critical angle. It's trapped inside. It has total internal reflection. And of course, eventually it gets to this rough surface. I just cut that with a saw, and so the light goes in all directions. And so you can kind of see how it's trapped in here. My laser is giving me a little bit of, or at least the switch, it's a hard time. But what I do like, and maybe even with the lights all the way off, maybe you can see it even better, is you can kind of see the light come out the side of it, which is actually an indication of this is a poor fiber optics. But that's what I kind of like about this. It's a poor fiber optics. The light coming out the side is for your visual effect. The truth is, you wouldn't really want that for a true fiber optics. But what makes this kind of nice is then if I take one of those plastic pieces and I heat it and bend it, I'm hoping you can kind of even see, even with the lights on, it goes up and it curves around, and most of it's coming out right here. Now, not all of it, some of it comes out here, so you can actually see it. That's why I was saying kind of the advantage of this cheap piece of plastic is it doesn't work well like a fiber. You can actually see the light coming out of the sides, so that way you can see that it's actually flowing through this, kind of like water flowing in the pipe. And I don't know, maybe in the dark it might even look better. And so there it is, as it kind of arches around, and most of it, like I said, comes out the end. Well, maybe I better jump to the main fiber then, because here, if I shine the light on this end, it'll go through this fiber optic network and out this end. Maybe you can see it better on camera if I switch it. So I'll do this end. So I'll put this end towards you. And if I then scan across here, can you see any flashes of light there, Ron? Okay, good. And so as they go through here, they'll arc around, and depending on whatever fiber I'm hitting, I really can't tell, they're so small, which one I'm hitting, but I know I'm hitting one of them at a time, and it will then flash on that other end. And so it's kind of my way of trying to illustrate here this total internal reflection and then this usefulness in our fiber optics. And so it's great. By the way, I said UCSB, but if I was getting some communication from, say, the University of Tokyo, then it would leave the server at UCSB. It would go back, out of their campus along the railroad track, go up to Morro Bay to another server. That's the AT&T server. From there, it would go to another fiber and go underground and under the water and go out to Hawaii. And from there, it would go back underwater and out to Japan. And so eventually, all these pulses of light are going to get out to that server out in Japan and say, hey, we would like to read this page, and so send all this data. And so all these flashes of light will go back under the Pacific and back up into the Morro Bay and to the AT&T servers, and then underground into the AT&T network along the train tracks, and then to the UCSB server, and then across our little fiber network across town here, and finally over to City College. And so that's the whole idea then of the fiber optics. Well, finally now, good, and I think our time is working out well, and we haven't really been kicked out of this room quite yet, and that's good, is now I can get to the grand finale, and the hardest part of this chapter is that just like we did for reflection, and we made mirrors, and then we could make our images, and we can make them bigger or smaller, real or virtual, we can do the same thing with our lenses. And so, let me clear off the board here, because I'd like to get all four scenarios up here. Just like I had all four scenarios for reflection, I can get all four scenarios for the refraction, that is for the lenses. And so I'll start with what I call the fun one. And just to remind you, the fun mirror was this mirror. Maybe I'll turn off the chalkboard lights. But we called this the concave mirror because it was curved inward. Notice it took the light and made it converge. Remember, the second mirror we did was this one. We called it convex because it had a convex shape to it and it made the light spread out. Okay, well, I'm going to take a lens, maybe stand back out here in the light. Not a mirror, but a lens. And in this case, the glass is curved. And just like a curved mirror, then the different rays at different part are going to curve a different amount. And here's where it gets a little more complicated than the mirror. It's going to curve again coming out. Even though it curves, or bends I should say, refracts on both surfaces, surface 1 and surface 2, the end result, the two together, is really what I want to focus my attention on here. So watch this lens. Now before I put it up here, what shall we call this lens? Well, since the glass bows out, let's call it a convex. This is a convex lens. Now I emphasize that because watch what happens. If I put this convex lens in here, do you see how it made the light converge? Do you see that this lens is behaving a lot like this mirror? And so if you understood the mirrors, I'm hoping you will also understand the lenses. I'm trying to say they're the same thing, except, be careful here, remember the mirrors reflect, the lenses refract. So their behavior is the same but reverse. Do you see it already? Watch. Which mirror made the light converge? Concave. Which lens makes the light converge? The convex. You see, the light goes through the lens, but reflects off the mirror. And because of that difference between reflection and refraction, the different shapes give you exactly the opposite. So the behavior of a convex lens is going to be the same as the behavior of a concave mirror. Did you catch that? That's why I like to call it the fun mirror, because I can also call this the fun lens. The fun lens does three different things. Just like the fun mirror does three different things. And they do the same three different things. So the ones that make the light converge are what I call the fun ones. They have the most variety of things you can do. The thing I got to keep emphasizing then is watch your wording. The concave mirror is the fun mirror. It makes the light converge. The convex lens is the fun lens. It's the one that gives us three options. All right. So let's talk about this one first. But as long as I'm trying to show you that distinction, let's do this. I don't know if you can see it because it's not curved much, but it's as much as I really need on the whiteboard. Look at this piece of glass. This glass is curved inward. It's narrower here than on the tops or the bottoms. And because it's curved this way, this is a concave lens. And how does a concave lens affect the light? Well, let's take a look up here. If I take this concave lens and I put it in here, see how it spreads the light out? It'd be nice if I had one that spread a little bit more. I don't think I do. I've got this one, but it's a little more confusing because it's not as big. It can only do the 3 beams at a time, and it's only concave on one side. So maybe I better just not mess with it and just show you that one. It spreads it out. And I'm hoping you see that the behavior of this lens, the concave lens, is a lot like the behavior of that convex mirror. Remember I called this the boring mirror? So I'm going to also call it the boring lens. And so the boring mirror only did one thing, right? The boring mirror made things smaller and upright. That's all it ever did. And that's exactly what we're going to see here for this lens. It's kind of boring. It always makes it right side up, and it always makes it smaller. And so these two are the same. I'll put them together. And then these two are the same. So I'll put them together. And so if we could take what we just learned in chapter 17 about the concave mirror, we're going to see that works for the convex lens. Same equations too. And the same thing over here. The concave lens behaves the same as the convex mirror. So this will have three interesting things with two different equations. And this will have one interesting thing with one different equation. And so really, and this is where I think I want to do a little bit more than your author. This is where your author says, they're the same. Let's just call it quits. We're done. But again, I think maybe going through the geometry a second time and going through the equations is worth it. Especially since we haven't got to our hour and a half yet and we're getting to the end of the chapter here. So I'll keep talking here, but more than that, show you. And again, let me start with the fun one here. So let me take the fun one. Actually, let me take the boring ones and make sure they're good and out of the way. Okay. So I'll bring the two fun ones here and I'll keep comparing them. But notice, right, it makes the light converge. Notice it makes the light converge. Although this reflects and this refracts. But either way, it makes it converge. And so let's do this again. Let's call this point the focal point, F. Let's do this also. The distance away, let's call it its focal length. Now, let me show you something where lenses are different than the mirrors. Because we said in the last chapter that the focal length would be half the radius of curvature for a mirror. And that's still true. That's true for the mirror. That is not true for the lens. The lens, because it actually has two surfaces together to make the overall effect, it is not just half of one surface and half of the other. No, no, no. Because the bending comes from not just the curvature of one, but two. And not just the two curvatures, but also what the material is made out of. So, the focal length is much, 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 much more complicated. It depends on what material it is. It depends on not only the curvature of this face, but the curvature of that one. And so the formula for the focal length, is going to take some calculus. So, next semester, or when you take Physics 123, I promise you, I will spend a little more time and we will work through how you get the equation. What you'll see is the equation is not so simple. It's not just half the radius. It's not just one radius, it's two radii, because it's both surfaces. And it's not just that, it's also what material it is. So you have the material that it's in, it has the material where it's come from, you have the radius of the first one, and you have the radius of the second one. All of those come into play. So because of that, your author says, look, let's just say it has a focal length. Let's not try to give you the equation of how it's related to anything, because it's just a little too much at this point. Okay, so here's some good news is you will never be asked to calculate the focal point of a lens. Now, you will for the mirror, I'll say it again. The mirror, it's half the radius of curvature. But for the lens, it's a much, much more complicated equation. Actually, the equation actually comes out pretty simple at the end, but it does involve a lot of calculus and trigonometry to get there. So because of that, your author and I will just say, this is the focal length. All right. So, in my case, if I were to actually measure the focal length of this one, I would just take the center of the lens and look out, and it looks like it's about 15 centimeters. I won't bother to work with a number, I'll just say F for the focal length, but it looks like it's 15. So I'll say it again, that right there is something very, very different between the lenses and the mirrors. The equation for finding the focal length is not just half of the curvature, because there's two curvatures. And there's the speed difference between one material and the other. So it has what material did it start in, what material did it go into, and then the radii of each of those surfaces. So there's four things we got to consider. Let me show you something else that's kind of fun about this mirror. I don't know if you could see in the camera, but did you notice this number, and it's upside down right now, the upside down 2? That upside down 2 then could be made right side up. Do you see the focal point is still at the same place? This is me a way of saying if the light goes left to right or right to left, it doesn't matter. If it hits surface 1 and then 2, or if it goes the other way, hits 2 and then 1, it doesn't matter which way it goes. The bending is caused by, and I'll say it again, both surfaces. So when you have a lens, it doesn't matter which way the light goes. This would be silly for me to do, but I could actually take my glasses off, turn them around, and they work just as good. It doesn't matter which way the light goes through my lens. Now, obviously, the way they're bent to match the curvature of my face, they don't fit well like this. But optically, they work exactly the same. And because of that, we like to do something a little different for the lenses than the mirrors, and that is if we put a convex lens, we will say that there is a focal point on each side. It doesn't matter if the light started on this side, it would go to this focal point.